Hi, my name's Dan, and this video is one of a short series of videos I'm doing on memory cells, in fact, otherwise known as bistables in digital electronics, which are fairly simple circuits that can remember state. That's part of a larger context of a set of videos that I'm doing that go from the principles of digital electronics and basic logic gates all the way through to creating a simple 4-bit CPU. Um, the roadmap for where I'm going with that is in the description down below, as is a link to the where you can get hold of this software, which is called Digital Works, which is digital simulation software, and it does almost everything that we want it to do. It's more visual and cheaper than actually using digital hardware to create this. I invite you to play along with me and create this CPU through this long series of videos. And the point that we're at is that we've just in this series done a thing called the D flip-flop, which is a basic memory cell which can take data in, and when the enable line is has a 1 come into it, it will then actively remember the state of the D line, the data line. What I've done here is, well, I want to talk about another version of the flip-flop, which builds on the SR flip-flop, the set reset, which is called a JK flip-flop. A JK flip-flop has a different solution to the fact that if we have both S and R high when the enable comes high, then when the enable comes low, we don't actually know what state, or is not determined by the logic what state our data is going to be in. And an SR flip-flop is kind of, a JK flip-flop is kind of created like this. This is one version where we've got the S linked up to an AND gate. We've got the R linked up to an AND gate. We've got our J and K. The letters J and K, I have no idea if they actually mean anything. I think they're just letters that happen not to be used elsewhere. So somebody decided to use them for this particular type of circuit. And we've got a crossover feedback, which is similar in some ways to the very basics of the SR latch, which is somewhere below the hood here. If we double click that and double click that, we've got this double crossover feedback thing going on. And we've got it this time using AND gates. Okay. And this is a macro that I created for a JK flip-flop. However, one of the reasons why I'm not kind of walking through the process of making this and not demonstrating it is because the JK flip-flop actually uses some of the characteristics of the silicon and the semiconductors to make it work properly, and I have found it difficult to create a JK flip-flop inside Digital Works and to get it to work correctly because of the differences between the simulation and the actual silicon and electronics. However, thankfully, Digital Works provides its own JK flip-flop. So what we're going to do is I'm going to just get rid of that, and I'm going to show you what a JK flip-flop does by using the built-in one that's part of Digital Works. And this is the only thing that I am going to use which is not a basic logic gate in the creation of this CPU. Is this JK flip-flop, which has been created for Digital Works because their version works, and that's exactly what I want to happen. So let's do a quick demonstration of this. I'm going to give us some inputs and a couple of outputs. And you'll actually see that it's got more inputs than you might expect because there's a couple of inputs down the bottom here that are not labelled, which I'll talk about in a few seconds. Let's just wire up these. So that's J at the top, K at the bottom, and then the clock, which is I've called enable in the ones that we've created. It's a kind of, it doesn't matter which of those two names is used, but I was going to pull that out so that we can see that it's distinct. Make sure we're simulating, and Um, off we go. So when this starts simulating, this one turns to not Q. And if we put J in, it's hopefully going to set. But there is something strange I remember about this one, is that it actually changes when the clock goes low, not when it goes high. So J works as S, K works as, let's disconnect that one, as a reset. So when it goes low, it'll switch back. Yes, thank you. It is doing what I said. And when we have them both high, every time it goes low, it switches. Okay, so this is different behavior from the SR flip-flop, different from the D flip-flop, and it actually does what you might call flipping and flopping. Sometimes this, in this state, this is called a T flip-flop or a toggle flip-flop. And sometimes all you want is for this T to happen, this toggle. And so you connect the both J and the K together and to a constant 1. And then you put a pulse in here. And in fact, let's do a little bit of a thing to show that. Let's change this from these inputs, and we can leave the outputs the same, which is fine. So this that's a constant 0. This is a constant 1, which is VCC, which basically means plus voltage. Kind of connect it to both those. And instead of doing this to the as an enable thing we can put up and down, I'm actually going to connect it to a clock to show this working. And that clock's running, and we can see as it goes, it switches between one and the other. And if we just consider the clock and we don't look at the not Q output, in fact, to help us do that, I'm going to get rid of that there. You might notice that the clock is flashing at um, 1 cycle per second, and our Q here is flashing at half a cycle per second, or in other words, 1 cycle every 2 seconds. So this JK flip-flop, when turned into what's called the T flip-flop, actually is a frequency halver. And this is quite useful. And in the next 2 videos, we're going to use this to develop a binary counter. So that's it from me for now.